Alright guys, this is an extra video for chapter 6, just working a few problems. So let's start off with the one at the top of this sheet, where basically I have an electron in a hydrogen atom that is going to drop from the n equals 3 to the n equals 2 energy levels. It wants to know how much energy is released when 1 mole of electrons do this transition. Okay? Well, the equations that we have calculate the energy or the wavelength for a single photon. So, anytime you see a problem that involves an electron dropping from one energy level to another energy level, you have to think about the Rydberg equation, which this equation is the Rydberg equation. It's on the formula sheet that I have posted. If you use this version of the Rydberg equation, lambda is your wavelength. Now notice that if you solve everything on the right side, you don't get the wavelength directly. You actually get 1 over lambda. So when you get your answer, then you have to do the reciprocal or the inverse of that value to get the true wavelength value. Or if you are solving for energy, then you can plug into this version, which is very similar. It's just the constant. Instead of the Rydberg constant, which is R sub h, we're using a different constant that's labeled B. Both of these constants are on the formula sheet, so you'd have to look in the appropriate place to find them. These are the two values that we would need. So when I look at the problem, the question wants to know how much energy is being released. So I would want to use the second version of this equation. I'm solving for the change in energy when the electron drops, so that's the value that I want. B is 2.18 times 10 to the minus 18th joules. 1 over NA squared minus 1 over NB squared. Sometimes the N values are labeled N1 and N2. It doesn't really matter. The key is the lower energy level should go in the front. The higher energy level should go in the back. That way, when you do the subtraction, we always want to get a positive E value, or above, we'd want to get a positive wavelength, because it wouldn't make any sense for the energy emitted to be negative or the wavelength of the light to be negative. So the N value is just the smaller one has to go in front because that gives you a positive answer. Okay? Now, so I'm going to plug in for this problem, plug in my B value right here, plug in my 2 for the second energy level as the first N value, and plug in 3 as my second N value. So it's going to be 2.18 times 10 to the minus 18 times 1 over 2 squared minus 1 over 3 squared, which will end up being 1/4 minus 1/9. So then if you can plug that in your calculator, I got that the answer for the energy, whether you call it E or delta E, is going to be 3.03 times 10 to the minus 19 joules. Okay, so the first part of the question, that's the answer. Actually, no, that's not the answer. That's the energy of 1 photon. So then I'm going to multiply that times Avogadro's number to get a mole of electrons. So I multiply by 6.02 times 10 to the 23rd. And that's going to give me the energy for an entire mole. I guess I can do that. Times 8. And I got 182,274. So let's just call that 182. That would be in joules. So change it into kilojoules. It should be about 182 kilojoules per mole. That's the value it's looking for. That would be the molar release of energy for this transition. Okay? Again, that's special to this problem. We wouldn't normally do this step unless it asked for how much energy is involved in a whole mole of electrons doing it. If I'm just looking for 1 electron or 1 photon, this would have been my answer for the problem. Okay? Now, next part of the problem, it says what's the wavelength? Well, if I have the energy, I kind of have two choices here. To get the wavelength, I could go back and plug into this equation and solve for the wavelength, but honestly I think that's more work. I would probably take the E value, and I know that E equals HC over lambda. So I would plug in my energy value right here, Planck's constant is 6.626 times 10 to the minus 34th. Speed of light is 3 times 10 to the 8th. And then I would solve for my wavelength. Okay? Once you get your wavelength there, I think if I remember right, it should come out to be about 650 or 660 nanometers, which would be 6.5, 6.6 times 10 to the minus 7 meters. But that is closer to the red side of the spectrum, so the color would probably be kind of orange or red. I don't expect you guys to memorize exactly what wavelength corresponds to each color. Just generally know that if you're closer to 700 nanometers, that's going to be red. If you're closer to 400 nanometers, that's going to be violet. And then if you're somewhere in between, you just make your best guess. Okay, so that's the end of that problem. So then we'll move on to the next one. And actually for the next one, I'm going to cut off and make a separate video because the next one involves the periodic table.